Alright, welcome to Chapter 4, Section 5, Summary of Curve Sketching. We're going to do a quick review of a lot of skills and tools that we already know and are aware of. So this will be a quick refresher, and then we're going to bring those tools and skills to bear on some equations in order to generate some graphs or some curves. So in order to do that, I'm going to start out in this video, as I often do, by going through some slides that are provided by Stewart in his calculus book, Early Transcendentals, 8th edition. And after going through these slides and just talking with them and putting some little notes on them, I will talk through the solution processes of a couple of questions provided in these slides by the author. And then I will also make a video where I go through from scratch some problems that are from a different online software. And I'll go through and talk about the thought process involved in order to graph those curves using the processes and tools and strategies that are discussed here in Stewart's notes. So the first thing that we want to be aware of when we're looking at our equations is the domain of whatever the function is that we're working with. You know how to find x and y intercepts, plugging in x values of 0 in order to find the y-intercept, and a y value of 0 to find an x-intercept or intercepts. Symmetry is determined by deciding or determining whether or not your function is even or odd. And we can take negative x, plug it in, and see if it's equal to our original function. That would tell us that it's an even function. And if it is an even function, then the symmetry that we see in the graph is about the y-axis. And if we have an odd function, which we can determine by taking negative x, plugging it in to our function, and seeing if it equals the opposite of our original function, then we're working with an odd function, and the graph will have symmetry through the origin, or it will look like one half of the graph has been rotated 180 degrees and placed down again, much like in this example graph here. And some examples of odd functions that you should be familiar with are y equals x. That definitely has symmetry through the origin, as does x cubed, x to any odd power. And the sine function, as you might recall from a pre-calculus class, is also an odd function. The sine function is also a periodic function, as are all of the trig functions. Here's an example of a less typical, perhaps, periodic function, and you can see that one segment of this graph, denoted by a period of p, can be repeated and occurs over and over again. I've never heard of a periodic function referred to as having translational symmetry, but I like that. If you translate it to the right p, in this case, if you translate it to the right p units, you have the same image again, much like copying and pasting to the left and to the right. Horizontal asymptotes you're familiar with. This is a different way of phrasing them from how you originally learned about horizontal asymptotes. Here this is sort of a limit description, so as our x values go really far to the right or really far to the left, do our y values consistently approach the same value as we go really far left and right, or perhaps those could be different y values that our graph approaches? If that's the case, then we do have a horizontal asymptote or a couple of asymptotes. As you go really far to the left or to the right, as your x values go to positive or negative infinity, if it turns out that your y value goes to positive or negative infinity, then you don't have an asymptote, but it could still be useful information, and I believe we will see an example of that later in these slides. A vertical asymptote you're most familiar with in rational functions. So after you simplify a rational function, if you have an instance of the variable still in the denominator, then that x value that causes the denominator to equal 0, or maybe multiple x values cause the denominator to equal 0, that's where we see a vertical asymptote. And as your x value approaches that sort of problematic or x value, or the 0 in your denominator from the right, your y values might go up to positive infinity or dive down to negative infinity. Or if we approach that particular x value from the left, your curve could go up on one side of that vertical asymptote and go down as you approach from the other side of the vertical asymptote. Excuse me. The most basic instance, I think, of that happening is this graph, y equals 1 over x. The reciprocal graph. Here, as you see the curve coming in toward an x value of 0 from the right, the curve is going in the upward direction toward positive infinity, or as you approach 0 from the left, you see the y values going down to negative infinity. So they don't always have to be approaching the same value, positive or negative infinity. If the domain is not infinite, then we should examine what's going on at the endpoints. We'll talk about slant asymptotes in a moment. Intervals of increase or decrease, we're going to be using the increasing-decreasing test, so we'll be looking at the first derivative. And we can determine maximums and minimums by seeing if our function is increasing to the left of one point and decreasing to the right of another of the same point, or vice versa. That'll help us determine if it is a maximum or minimum. The second derivative, of course, can also be helpful determining if it's a maximum or minimum. It can also be used to investigate concavity, generally speaking. And of course, somewhere where we have a change in concavity is referred to as an inflection point. However, there has to actually be a point at the given x value where the change in concavity happens in order for it to be an inflection point. Otherwise, if matter of fact, in this graph over here, you see that our curve in the third quadrant is concave down, and in the first quadrant it's concave up. And where is that change in concavity happening? It's happening right here. Well, what's the x-coordinate on the y-axis? That has an x value of 0. So do I have an inflection point at x equals 0? No, I do not, because my function is not defined where x equals 0. 0 is not in the domain. So an example of where we have a change in concavity, but no actual inflection point that we could give using an ordered pair x comma y. And then we start sketching the curve. You might want to rewind right now, go back toward the beginning of the video and make yourself a list of those different steps that we're going to go through, different characteristics of our functions that we're going to march through and take notes on in order to help draw the most accurate sketch of the curve that we can. It's not going to be precisely accurate, it is going to be a sketch, but it's going to have some key points on it. And this would be a great free response question for your teacher or professor to give to you, and they could ask you to point out some key locations and key characteristics. And this is a pretty comprehensive list. Matter of fact, I mean, there are other things on this page, but I went through and made my list, so I also have some problems worked out on this page, but come up with an organized way to go through those. And here we have our first example. So we're looking at this rational function. Part A says that the domain is, let me switch colors here, the set of x values such that the denominator does not equal 0. So we want to make sure that we're avoiding division by 0, and if we take this and solve it for x, we end up with a statement that says x is not allowed to equal positive or negative 1. Here's that same domain using interval notation. I will leave it to you to do the arithmetic of plugging in an x value of 0 or a y value of 0 in order to determine that the x and y intercepts are both 0. So the graph of this function will be passing through the origin. You can already see that we're accumulating some characteristics. The fact that positive and negative 1 would cause division by 0 leads me to believe that we're probably going to be seeing vertical asymptotes, and those are going to become part of our graph. We can already plot a point at 0, 0, so we have our first point on our graph. Excuse me. Since f of negative x equals f of positive x, the function is even and will be symmetric about the y-axis. If you plug in a negative x value into the numerator, anything negative squared is going to become positive. Plug in negative x here, squared, it's going to become positive, and we'll have our original function again. So it's definitely an even function. And that symmetry is going to help us. We'll only have to graph half of the graph, and the symmetry will give us the other half. Here we're looking at the limit as x is going to both positive and negative infinity. We're looking at those at the same time because, as we just talked about, the function's an even function. So plugging in a really large positive or negative value isn't going to matter. It's going to return the same y value. And in this case, looking at the horizontal, or looking for the horizontal asymptote using limits, in order to evaluate this limit, ideally what we should do is divide both numerator and denominator by the denominator's variable to the largest power, which here is x squared. So let's do a quick bit of division in the numerator and denominator. We have the limit as x approaches positive or negative infinity of 2x squared over x squared divided by our denominator, x squared minus 1. We're going to divide that by x squared also, and I'm going to distribute my division right away, dividing both terms in the denominator by x squared. If we simplify this fraction, the x squareds in the numerator are going to cancel, leaving us just with a 2. And in the denominator, x squared divided by x squared certainly reduces to a 1. There's the minus sign, and nothing to be done about 1 divided by x squared, so we're stuck with that. And then, if we apply the limit, I should have had this limit written in right there also. Sorry about that. To be totally correct, we should be rewriting the limit portion of the statement as we go along after each of the equal signs. If we evaluate the limit of this function, however, the 2 remains, the 1 in the denominator, and almost by direct substitution we can see that this fraction is going to go to 0. So we've got 2 divided by 1, which is equal to 2, and that's how we're getting this 2 right here. So our horizontal asymptote is y equals 2. We talked earlier about our denominator being equal to 0 when x is equal to positive or negative 1, and so there will be vertical asymptotes there. The question is, what is my graph doing on either side of those vertical asymptotes? So first of all, we're investigating what's happening as we approach an x-coordinate of 1 from the positive side and from the negative side, and you see that the curve is going to be approaching the 2 different infinities. One's curving up, one's curving down. And as our next x value is approaching negative 1 from the positive side, our curve will dive down toward negative infinity, whereas approaching an x value of negative 1 from the left, the curve will curve up toward positive infinity. So we've got some different activity happening on either sides of those vertical asymptotes. So here we have a preliminary sketch. We're just taking the things that we've noticed so far and putting them onto our sketch. Here's our horizontal asymptote of y equals 2 as a dashed line. You can see the dashed vertical asymptotes also. And right here, as we approach x equals -1 from the left, our curve is going up toward positive infinity. Down here, let's zoom in just a little bit. Down here we can see our curve as we approach x equals -1 from the right is going down toward negative infinity. We could put a little arrow on this one maybe. The author had that drawn already, but we can see the motion a little bit better. Similarly, as we approach x equals +1 from the left, our curve is going down, and up in the first quadrant, approaching x equals +1 from the right, our curve is going up toward positive infinity. Put a little arrow on there. Okay. Because this motion is happening here in the first and second quadrants, we're definitely above our horizontal asymptote of y equals +2. Isn't it therefore reasonable to assume that as our x values become large, that we're going to stay above this dashed line, above this horizontal asymptote, both in the first quadrant and in the second quadrant as we go out toward negative infinity? Again, isn't it reasonable to assume that we're going to stay above that horizontal asymptote? It's not always the case that a curve stays on one side of a horizontal asymptote. Horizontal asymptotes are all about what happens at infinity, or as we approach positive or negative infinity. Not so much what's happening when we're pretty close to the origin or close to an x value of 0. So this line being y equals 2, vertically we have some scale. This is surely approximately a y value of 1. But in the x direction, well, we've got this x value of 1 here, and 2, and 3, and 4. But I don't really know that my line is going to get that close to y equals 2 at approximately an x value of, I think we're at 5 out here. It's a little bit difficult to tell. Is it possible that this curve could actually come down here like this, cross the horizontal asymptote, and then come up along the horizontal asymptote and sort of be skimming along the bottom of it, approaching 1.9999999 as a y value? Is it possible? Well, it's possible. That could happen. Is it possible also that this curve comes down here, dips down below the horizontal asymptote, comes back up, and then connects and skims along the top of that horizontal asymptote? It's possible. Does it happen here in this graph? I'll tell you that it doesn't, and in a very short while I'm going to prove to you that it doesn't. See me building suspense there? Let's keep going through the different characteristics that we're examining. Here we're taking the first derivative, and it's been simplified for us. That's nice. Since the first derivative is greater than 0 when our x values are less than 0, how do we know that? We know that because this denominator, because it's being squared, is always going to be positive. So the sign of this fraction is going to be entirely determined by what's happening in the numerator. The factor of -4 is multiplying this factor of x. So when we're working with negative x values, this numerator is going to be a negative times a negative, which makes a positive. Therefore, our first derivative is going to be greater than 0 whenever we're using negative x values. The x value that we're going to be skipping over, however, is the one that would cause the denominator to equal 0. We know that there's an asymptote there, vertical asymptote. The function's not even defined, that x equals -1, so we'll hop over that one. When we're working with x values that are greater than 0, let's see, let me delete a little bit of that before we end up with too much. When our x values are greater than 0, in other words positive, we'll have positive times negative, which makes negative. Therefore, our first derivative is going to be less than 0 whenever we have x values greater than 0, skipping over, for the same reason, our x value of positive 1. Therefore, we can say that our function is increasing on these two intervals, and you see that we're skipping over that x value of negative 1, and it's decreasing because our first derivative is negative on these two intervals, and you see us skipping over the positive 1. Alright, so part of our graph is increasing and part of it's decreasing. That's good to know. The only critical number that we're seeing here is 0. So the critical number is where we're changing from our function being increasing, in this case, from left to right, increasing, it's changing to decreasing at the x value of 0. Look, here it is. This is the one number that they have in common, increasing and decreasing. Parentheses on those, so we're skipping over the 0 value in those two intervals, because at 0 it's neither increasing nor decreasing. F prime is equal to 0 when x equals 0. Therefore, we have a horizontal tangent line to our curve at the point where x equals 0. Since we're changing from increasing to decreasing when x equals 0, we can say that that is a local maximum. We're changing again from increasing to decreasing. That looks like we're right at the top of a hill, perhaps, which would make this point here a maximum. We could also run that through our second derivative test, and see if we're concave down, which we should be at the point where x is equal to 0. Also, the maximum value, or that particular local maximum value, is 0. And we determined that by taking the x-coordinate and plugging it into the original function. So the x-coordinate is when our local maximum occurred, and the y value answers the question, what is that local maximum? Again, when is the local maximum? What is the local maximum? And on the next slide, we're taking the second derivative. The author has done that for us and simplified. And here, we notice that our numerator is going to be greater than 0 for all x, because 12 is positive. X squared is guaranteed to be positive. We're adding a positive number. Positive times positive plus positive. I think we're looking at greater than 0. The denominator, however, being cubed, could be positive or negative. This statement says that our second derivative is going to be greater than 0 as long as this factor is greater than 0. If we take a value that's greater than 0, we cube it, we're going to get a number that's greater than 0 still. What x values will sort of force that to happen? What x values are going to cause x squared minus 1 to be greater than 0? I'm a visual person. For as bad as my handwriting it is, and my arrows, I mean, look at these arrows. These are sad arrows. So I might not have the steadiest hand, but I am still a very visual person. And when I see x squared minus 1, my mind goes directly to a parabola that's concave up, that's been shifted down 1 unit. So this point right here would be at -1, which means that this is at +1. I know that just from having worked with enough basic parabolas. So x squared shifted down 1 unit. And my question to you is, when is this graph, oops, let me try that again. When is this graph greater than 0? The answer to that question is where on this graph are my y values greater than 0? And that would be, I'm going to change colors. The yellow is just so much more visual, or so much more visible, I think. Here and here, all the points on that portion of the graph have y values that are greater than 0. When do those points on the graph occur? They occur when x is less than -1, and for points that have x values that are greater than +1. What's the most concise way to say that I need my x values to be strictly less than -1 and strictly greater than +1? That statement right there. That tells us when x squared minus 1 is going to be greater than 0. Alright, so my second derivative is going to be positive when my x values are not between plus or minus 1. They need to be on the outsides of positive and -1. Therefore, we can safely say that our second derivative will be less than 0 when our x value is between positive and -1. This compound inequality right here says that x is between negative and +1. Alright, it could be rewritten as that compound inequality. So our curve is going to be concave upward for these outer portions, the left and right hand sides of the graph, so to speak, and our graph is going to be concave down in the middle, so to speak, between x values of negative and +1. Normally, when we change, we mentioned this earlier, when we change from being concave down to concave up, or vice versa, we call that an inflection point. However, we don't have any inflection points here because the space between the timing when we change from concave up to concave down is actually at an asymptote. So our function is not defined at positive and -1, therefore we can't call those inflection points. However, those are when our inflection, or rather when our concavity changes. And we're seeing it here in this final sketch of the graph. This is when the concavity is changing at x equals -1. This is when the concavity is changing also at +1, x equals +1. Here we're concave up. Here we're concave down. Here we're concave up. We do see the graph skimming along the horizontal asymptote there. And it's not actually marked on here, but we do have that defined point that we saw of 0, 0. And as I told you, I would mention that it is not possible for this graph to be coming down our vertical asymptote, dip down below the horizontal asymptote, come back up, and then start skimming along the horizontal axis, or horizontal asymptote rather. That can't happen because we just demonstrated that this function is concave up everywhere to the right of x equals +1. This has to be concave up everywhere. The blue curve that I just drew in here is concave down right here. Not possible. We just demonstrated that that's not possible using the second derivative. That couldn't happen over here either. This has to be concave up all the way out to -infinity. All right. That's a lot, right? So we're drawing on a lot of information, not just from our studies of Calculus 1. We've got a little bit of pre-calc coming in there. We looked at symmetry, which goes back to college algebra, examining rational functions. That's a pretty good start. Let's see what else the author has in store for us on the following slides. We're talking about slant asymptotes here. I like this definition of, or a way of confirming that we do indeed have a slant asymptote. What's being said here is that as our graph goes off to the right, in this case, I need another color. What about, how visible is this? Oh, that's pretty distinct. No, it's not. It's almost identical to this one. They might even be identical. Maybe we'll stay with red. That works. As these two graphs or curves go off to the right, the actual curve that's in blue here is coming out, and y equals mx plus b is what's being suggested as our slant asymptote. And we can confirm that it's a slant asymptote if, as we continue moving to the right, if the vertical distance between our two graphs approaches 0, they're getting closer and closer together, but they don't actually merge, then it is indeed a slant asymptote. So again, the difference between the y values of those two curves. This is an x value. This is a y value. Again, this is an x value, but this is a y value. So we've got the difference between those two y values, and it doesn't matter which order they appear. We could just as easily swap these, because if we're finding the difference between them, whether we're approaching a value of 0 from the slightly negative side or slightly positive side, doesn't matter. We're going to be approaching 0. And if that's happening, then we've got ourselves a slant asymptote. A similar situation happens if we're heading out toward an x value of negative infinity. As a reminder, if you're working with a rational function, a slant asymptote happens if the degree of the numerator is 1 more than the degree of the denominator. 1 and only 1. And you can then find the equation of the slant asymptote by doing a long division. And here in this next example, we won't go into it in as much detail, but there are some little nuances that I do want to mention here. The first being that because x squared is positive and plus 1 is also positive, we have no danger of division by 0, therefore there will be no vertical asymptotes, and our domain is all real numbers from negative to positive infinity. I leave it to you to plug in x value and y value of 0 in order to determine the intercepts. You'll find out that this graph also passes through the point 0, 0, because the x and y intercepts are both 0. This function, the previous function, was an even function and therefore exhibited symmetry about the y-axis. This one is an odd function, so it will be symmetric about the origin. And earlier in these slides, we saw some examples of functions that are symmetric about the origin, like the sine function. Plugging in a value of negative x into our function, a negative number cubed remains negative. A negative number squared would become positive. Does that indeed equal negative f of x? It sure does. So this is definitely an odd function, and it will be symmetric about the origin. Part D, we already commented on that. As our function goes toward positive infinity, or sorry, this is written backwards from how I would normally say it. As our x values approach positive infinity, our y values also approach positive infinity. As we head off to the left, our y values go down toward negative infinity. So there's no horizontal asymptote. In order to have a horizontal asymptote, we would have wanted the degree of the numerator and denominator to be the same, or for the denominator to be of degree larger than the numerator. If we perform the long division, which we're doing because the degree of the numerator is 3 and the degree of the denominator is 2, so the degree of the numerator is 1 larger than that of the denominator, therefore we probably have a slant asymptote. We do the long division, we get this as the result. This also says x plus or minus 0 minus x over x squared minus 1. So we have plus 1. So there's this remainder that's happening down here. This is the proposed equation of our slant asymptote, so you could do that using long division. Can't do it using synthetic division because you're dividing by a second degree polynomial down there. And with this being the proposed slant asymptote, here, farther down, we're finding the difference between those two y values, f of x minus x. That arithmetic has been done for us, right? Because we know what f of x is, so that's been substituted into here. And then our proposed slant asymptote is that x value. We do the arithmetic, we end up with this fraction. We take the limit as x is approaching positive infinity and negative infinity, and either way, we end up with a value of 0, which means that the difference between those y values is tending towards 0, which confirms that y equals x is the slant asymptote. So it was a candidate, and now it's a finalist. So y equals x is the slant asymptote. In part E, we're taking the first derivative. Simplification has been done for us there. F prime is greater than 0 for all x values except 0, because f prime equals 0 when x equals 0. Just plug yourself a 0 in for that x right there and see what happens. I think you'll find that f prime is equal to 0. Therefore, since it's increasing everywhere except for at 0, I wonder what that's going to look like. Okay, so f prime, but if you were being asked for the intervals on which the function is increasing, I should be a little bit more specific with part E. Since it's increasing for all x values except 0, we would want to say that it's increasing on the interval from negative infinity up to 0, or you could choose x values from 0 up to positive infinity. So this would answer, if the question were, on what intervals is your function increasing? Those are your two intervals. Either joined by the union symbol or separated by a comma, depends on how the question is phrased. So f prime is equal to 0 at 0, which means we have a horizontal tangent line at that point. However, f prime is not changing sign. And since our first derivative is not changing sign at 0, we can draw the conclusion that there is no local maximum or minimum at that point. Let's check out f double prime, our second derivative. Quotient rule was performed, and then simplification done, giving us this rational expression. F double prime of our function is equal to 0 when x equals 0, positive, or negative root 3. We determine that by taking the numerator, really, and setting it equal to 0. So that's how we came up with those three x values. And this author likes to set up a chart in order to determine concavity. So we know where the second derivative is equal to 0. That doesn't tell us anything about concavity. We either need the second derivative to be greater than 0, which indicates concave up, or less than 0, and therefore concave down. Positive or negative, greater than 0 or less than 0. The second derivative is comprised of this factor of 2x, or just the x. Well, let's keep the 2 in there, 2x. This factor here, and this factor down here. And there's no danger of this factor being negative because the x squared is going to make the input value positive, plus 1 still positive, cubed positive. So remember we're looking at those three factors, and the way that I'm going to crop this, I might have been off the screen, so let me come back down and say one more time. that these are the three factors that make up the second derivative. They're listed here. They make up the second derivative. Let's choose an x value that is to the left of or less than our lowest x value for which we had a second derivative equal to 0. It might be a critical value. We might be changing concavity at that point. Let's figure it out. What's going on with the concavity to the left of our x value of negative root 3? Well, if I take negative square root of 3 is like negative 1.7, I think, something like that. Let's use an x value of negative 2. If I take a negative 2 and I plug it into here, it's going to be negative. It's negative 2. If I take negative 2 and I plug it into here, negative 2 squared is positive 4, 3 minus 4 is negative 1. I don't really care about the 1, but I care that it's negative. And if I take negative 2 and I plug it into here, negative 2 squared, positive 4, plus 1, 5 cubed. It's 125, but I don't care. It's a positive number cubed, which is positive. Now, remember that those are the three factors that make up our second derivative. What is a negative number times a negative number, that's positive, divided by a positive number? Still positive. Therefore, our second derivative is positive on the interval to the left of negative rad 3. Let's go through the same process, choosing a test value, an x value that's between negative root 3 and 0. So now we're on this interval. If we go through that same process, you'll find that x remains negative, this factor becomes positive, this one we know is always going to be positive, negative times positive is negative, divided by positive is still negative, therefore on that interval our second derivative is negative. The negative second derivative tells us that our curve is concave down on that interval. The second derivative here being positive means that it was concave up on that interval. So going through in whatever kind of an organized fashion you want to, in order to figure out where your curve is going to be concave up and concave down, that's what's going to help you determine inflection points, points where we're changing concavity. Here we don't have any vertical asymptotes, so we are actually, in this case, going to have inflection points, not just vertical asymptotes that separate parts of our graph, which are concave up and concave down. We have actual points where we aren't concave up nor concave down. Those are the points where our second derivative was equal to 0. When do those points happen? When x equals those three values. What is happening at those three x values? What's happening is that we have these three corresponding y values. So when you're asked for inflection points, if your function is actually defined for those x values, you'll probably need to answer using ordered pairs x comma y to answer what are or where are my inflection points. And here we are looking at the graph. This is our last slide, so I can't move it up any farther than that. I can zoom in a little bit and slide it up. Notice the inflection points are being pointed out. Look at the concave down and concave up parts of our graph. We're neither concave up nor concave down here. And in fact, we're concave up here and concave down out here. So those were our three different inflection points. Let me redraw those a little bit more accurately. So our three different inflection points were sort of chopping up our graph into four different intervals, and the four different intervals were concave up, concave down, concave up, and concave down, and the inflection points are the points where concavity was changing. That's why we get to call them inflection points. We can also see the slant asymptote is in there with the equation y equals x. And we had that point that we noticed very early on of 0, 0 being on our graph. All right, I'm going to chop this section or this discussion up into 2 separate videos this time. So that is the end of my review of Stewart's slides. I thank you very much for joining me, and if you would like to continue on, you can click into the subsequent video where I'm going to go in again and look at some homework problems that I'm going to assign to my students and talk through this process again on a couple of separate problems. We'll take it from scratch. Thanks so much. See you next time.